So again, chapter 6 here, what we are getting into is intermolecular forces. That is the attractive forces that exist between particles of a substance or particles of a mixture. And so I actually want to start off here with a question. And the question is a simple one. What is it that holds the sample of a substance together? All right, last chance to get something in. Okay, so our answers are largely falling into two different kinds of categories. We have the people that say intermolecular forces. Those people are the ones who are correct. Now, whether they know what those are, if they just read the title of the previous slide, we'll find out in a few seconds. And then we have the people that are talking about bonds and bonding. And they're not correct, but they're coming off of an idea that's not incorrect. So let's get into what the answer is. The answer is intermolecular forces. Intermolecular forces are the forces of attraction that exist between molecules of a substance and other molecules of that same substance. Now, for those of you that were thinking of bonding, bonding is what we call an intramolecular force. Those are the forces within a molecule. Now, it can be difficult because intramolecular and intermolecular sound really close to the same to each other. How do we tell the difference? How do we know which one is which? How many of you have ever competed in any kind of sporting event or other kind of extracurricular against other schools, universities, high schools, middle schools, primary schools, whatever? Right. Congratulations, you are all interscholastic athletes or students. Inter, I-N-T-E-R, indicates some kind of relationship between multiple, in this case, schools. For those of you that follow college basketball, last night was the women's national championship for intercollegiate athletics. Tonight is the men's championship for intercollegiate athletics. It's not North Carolina playing against other kids from North Carolina tonight. It's North Carolina playing against Kansas. There are two different schools playing against each other. How many of you have ever been in a gym class and had to play basketball? Okay, like it or not, that is an intra-scholastic activity. You're not playing against kids from the next town over. You're playing with kids, again, in your own school. Same thing with intramural athletics. You compete in intramural bowling. You're not playing against other students. You're playing against the students from Wabash Valley College and Lincoln Trail. You're competing against other VU students. That's an intra-scholastic activity. So the difference between the terms has to do with where those interactions are taking place. Intramolecular forces are happening within the molecule. We know them better as bonds. Intermolecular forces are occurring between molecules and other molecules. Is an experience outside of the molecule itself. Now, as far as these are concerned, again, intramolecular, we're talking about bonding forces in an attractive sense, or repulsive forces in a non-attractive sense. So again, think about those diagrams that we showed you in chapters 4 and so on, about the idea that you get those nuclei a certain distance apart, they form a bond, the attraction is maximum with minimal repulsion. You get them too close to each other, the nuclei start to clash, the bond isn't as strong. Now, one thing about intermolecular forces, the forces that exist between molecules are not as strong as the forces within the molecules themselves. It is going to take far less energy to break an intermolecular force as compared to an intramolecular force. The amount of energy necessary to break a bond is far greater than the energy to separate two molecules from each other. The other thing that we have to know is that these forces are over long distances, which means there is a length component to them. The closer that they can get to each other, the greater the intermolecular force is going to be. The more distant they are, the weaker that intermolecular force is going to be. That's something that you're going to want to kind of file in your memory bank, because when we start to compare different types of forces to each other, that is going to be one of the contributing factors. These intermolecular forces, these are the ones that are going to ultimately be responsible for a lot of the physical properties. Things like melting point, boiling point, other properties that you'll see discussed, vapor pressure, viscosity, ability to dissolve in water. So when it comes to these types of intermolecular forces, which now that we've established the difference, we're not going to keep trying to go through the dictation exercise of saying intermolecular force every single time. We're just going to call them IMFs from now on. As far as IMFs are concerned, we can break it down into two groups, basically. The polar forces, these are the ones that exist in polar molecules. And the nonpolar forces, the ones that exist in nonpolar molecules. So because of this, we can see why we had to do that bit with molecular polarity in chapter 5. If we can't establish something as being polar or nonpolar, it's going to be very difficult to establish what kinds of intermolecular forces exist within it. Now, inside of those polar forces, we've got three different types. We've got the dipole-dipole forces, the hydrogen bonds, the ion dipole forces. We'll talk about each of those individually later. Same thing for the nonpolars. Nonpolars primarily fall into what are called London dispersion forces. But there is another force in there called an induced dipole. And again, we'll talk about that more when its time comes. Well, we're going to start with the polar forces. And the primary reason is because polar forces are going to be the ones that we spend the most time with in this class. Almost everything that we've been dealing with thus far has been water-based, and we know that water is a polar molecule. So everything that interacts with water is also going to be a polar molecule as well. What makes them polar? Well, they have to have within it something called a permanent dipole. Permanent dipoles, you remember, are just those molecules that happen to have a certain level of asymmetry in their geometry. That's what we look for in those polar molecules themselves. So again, going back about a week to where we were last Wednesday, this is all about identification. Can we identify asymmetrical molecules based upon their three-dimensional shape? If we can, those asymmetrical molecules are polar. They have a permanent dipole. They have an area that is always slightly negative and always slightly positive. Now, it's important to contextualize what that polarity gets us. Again, as far as attraction is concerned, polar forces are going to be weaker than any kind of bonding. We already know kind of the hierarchy of bonding. Ionic bonds are way stronger than covalent bonds. And the reason we know that is we can take any solid that is covalent and we can melt it pretty easily, with some limited exceptions. Whereas an ionic crystal, how hard is it to melt a salt? Pretty hard. So we know from that ionic has a much greater level of attraction than covalent does. But polar is significantly less than even covalent. But polar does have a greater level of attraction than nonpolar does. So when we consider attractions within molecules, we have to understand polar interactions are going to be stronger than nonpolar interactions. That's also going to be one of the reasons why we don't see crossover between polars and nonpolars. Because the polars are going to be way more attracted to themselves than they would ever be to the nonpolars trying to mix their way in. So they're just going to stay where they're more stable. So kind of the baseline for a polar interaction is something called a dipole-dipole interaction. In a dipole-dipole interaction, we have a polar zone that is slightly negative and a nonpolar zone that is slightly positive. Now, what are those funny looking S things that I just drew? Well, that's the best representation I have for the lowercase Greek letter delta. The Greek letter delta represents a partial charge. So we're not dealing with fully positive one and fully negative one here. We're dealing with less than that in some capacity. The deltas, delta positive and delta negative, tell us that there's charge here, but it's less than positive one, it's less than negative one. But because of this dipole moment, the fact that we have this negative area and this positive area, and that negative area and positive area are always there, they can attract each other. The negative can attract the positives can attract the negatives. And while it isn't as good as an ionic bond, and it's not even as good as a covalent bond, there is still a level of attraction there that is noteworthy. It's going to draw these molecules together and make them just a little bit harder to separate. And what that means in terms of physical properties is that it's going to require just a little bit more energy to contract phase changes. Higher boiling points, higher melting points come as a result of that. Now, there's another way to show polarity is through the use of an arrow. So I don't know if it's going to show up in the drawing here, so I'm going to draw it off to the side. If you see arrows that look like that, that is an arrow showing polarity, either in a bond or in an overall molecule. The convention here, again, the positive tail of that arrow is pointing to the positive end of the molecule. The head of the arrow is pointing to the negative side of the molecule itself. So this is another way of showing a dipole moment. Okay, so that's dipole-dipole. Dipole-dipole forces exist in all polar molecules. Doesn't matter what kind of polar molecule it is, it's going to have dipole-dipole forces in it. Now, for some, dipole-dipole is not going to be the only kind of force that exists. Hydrogen bonding is a specialized form of dipole-dipole force. What we find in hydrogen bonding is not only do we have a dipole, not only do we have a separation of charge, but we almost have it to an extreme level, because what we see are bonds to these highly electronegative yet small atoms: nitrogen, oxygen, fluorine. If you look on that electronegativity scale, you'll find that those three elements are the three elements that have the highest electronegativity values. They also happen to be the three smallest atoms as well. So because of that combination of factors, we've got a very polar bond, and that polarity is distributed over a very small area. We have extremes in polarity. And those extremes in polarity are going to give us extra strong interactions. but there are some rules with that. First of all, we have to have a polar molecule. And merely having one of those three atoms in it is not enough. That atom has to be bonded to a hydrogen. That's why it's called a hydrogen bond. So if I meet both of those criteria, not only do I have a polar bond, not only do I have dipole-dipole forces, I have dipole-dipole forces and hydrogen bonding. And that's going to make that intermolecular force that exists in water, that intermolecular force that exists in ammonia, just that much stronger, that much harder to break apart. There are many applications of hydrogen bonding. Most of them have to deal with water, but there is an important biological example as well. Those bonds that we say that exist between the two opposing strands of DNA, those bonds are actually hydrogen bonds. They are not covalent. Now, it's important that they're hydrogen bonds because, again, if you think about the function of DNA and what its purpose is, it holds all of your genetic material, yes, but it also needs to be replicated, which means we have to be able to separate those strands from each other so that we can replicate each strand. Well, if there are covalent bonds there, that requires a ton of energy to do. But since they're hydrogen bonds, yes, they're strong enough to hold the strands together. They're also weak enough that when the time's right, zip, we can unzip the DNA and replicate. Now, there is one other polar interaction here. Where we see this polar interaction is primarily with water. And not just primarily with water, but water that is creating a solution with an ionic compound. It's called an ion-dipole interaction. And so naturally, what you would expect out of an ion-dipole interaction is you have to have an ionic compound and you have to have some kind of a polar solvent. And that polar solvent is usually, doesn't have to be, but it's usually water. Now, of the three polar interactions that I described, this one is the strongest. And the reason why it's the strongest is because we're not just talking about the attraction of partial positive charges to partial negative charges anymore. An ion has complete charge. It is completely +1, completely +2, completely -1, whatever the case may be. So its ability to attract polar molecules to itself is considerably higher because of the magnitude of its charge. And so what we end up seeing is that these molecules are capable of, these ions are capable of attracting far more than just, oh, I've got a couple of waters around me. Because that's kind of how water is. Water can attract a couple of water molecules to itself, but it kind of ends there. We can see that this cation here is attracting 6 waters in what is called its inner sphere of hydration. And that each of those waters is attracting at least 1, if not 2 more water molecules to itself. That's called the outer sphere of hydration. So I want you to kind of burn these images into your memory because they are important. They are what ultimately describes why water is able to dissolve so much stuff. Because again, if we think about it from an attraction standpoint, ionic compounds are way at the end of the spectrum. They are super attracted to each other. And polar intermolecular forces, while attractive, are not nearly as attractive as ionic bonds. And yet, water is able to dissolve ionic compounds. Why? Because collectively, it gets a greater level of attraction from all of those water molecules sticking to it than it does from the ionic bond. So that's enough to overcome it. Now, note also, not every ionic compound does this. This is why we have solubility rules. Some, based upon what ions are in them, the ions are more attracted to each other, the water doesn't penetrate, it doesn't break in. But for most, we see this breaking apart taking place because the water creates enough total attraction to overcome the ionic bond being broken. But I want you to burn these in your memory because you're going to see them again. And so what's important for you to note, look at how everything is kind of pointing itself in the right direction. For the negative ion here, look at how each of those waters, they're not randomly just going around that negative ion. They're all pointing in a very particular direction. Hydrogen in. Why hydrogen in? That's the side that's positive. So the positive side of the water is attracting the negative side of the ion. And if you look at the positive ion, look how they're oriented. It's not just any old direction. It's oxygen in. Because the negative side of the oxygen is attracted to the positive ion. So those are the polar interactions. Let's look at the nonpolar interactions. And first and foremost on this list of nonpolar interactions are the dispersion forces, also known as the London dispersion forces. These are attractions that are caused by the formation of what are called temporary dipoles. Now, a temporary dipole is just a moment of time where the electrons in the atom or the molecule have moved around to the point where we can see that there is a separation. All right, everybody stand up. All right, when I say go, I want you to move around the room for 10 seconds. I'll tell you to stop. All right, and go. Stop. Okay, you've just created a dipole. There are 4, 7, 11 of you over here. There are 6 of you over here. There is a greater density of students on this side of the room compared to this side of the room. Now go back to your seats. Now, we've got 8 on this side, 9 on this side. It's about as even as it's going to get for 17 people. That's what happens in molecules. The electrons are moving around overall. And there are going to be moments in time where there are electrons that are heavier on one side than on the other. That's a temporary dipole. Now, just as within 30 seconds, we were able to get to one configuration where we were separate, and then back to a configuration where we were even, it works just as fast in molecules as well. And that's why they are temporary dipoles. They're based on random motion of electrons. They don't exist for very long periods of time. But while they're there, they can force the other molecules around them to also experience that same kind of distortion. Let's imagine that there was a classroom right next door. In that moment where there were more of you over here, the repulsion of those electrons would force more electrons in that other room to go to the other side. And so you'd have a negative side on here, a positive side on the other. There'd be a brief attraction between the two. That's the intermolecular force at play. Now, London forces are also governed by another idea. This is an idea called polarizability. Polarizability is basically how easy is it to create these temporary distortions. And there are 2 factors that generally go into that. First of them is number of electrons. The more students I add into this room, the more likely it is from a probability standpoint that I'll have even the slightest distortion at any one given moment. Right now, there are 17 of you sitting there. By the very nature of having an odd number, we're going to have a slight distortion. But if I added 17 more students in here, and I didn't need 8 on one side and 9 on the other to get a distortion, I just needed 18 and 16, it'd be a lot easier to get that. The more we add, the more likely it is we'll get a distortion. Now, counting the number of electrons can be a pain, but we can estimate number of electrons through molar mass. The heavier something is, the more electrons it's going to have the more likely it is to be distorted. So this diagram is kind of showing the same thing that we just kind of illustrated ourselves. If a temporary dipole is to form, we can see that it's really hard on this color map, but there is a slightly negative end here and a slightly positive end here, and that's going to force the other atom, the other molecule to do the same thing. But again, momentary. Happens, they attract, they go back. So as you might expect, these forces, because the distortions are not very large, so we don't have very big charges to deal with in the first place, and because they are temporary, these are very momentary kinds of attractions. They're not very strong. Now, this is slightly different from what is called an induced dipole. An induced dipole happens when a polar object comes into the area of a nonpolar object, and that nonpolar object distorts itself, changes its shape slightly to accommodate an attraction. Most common example of this is water and dissolved gases like oxygen. How does oxygen get dissolved into water so that things can actually live underwater? Well, if we look at it from a pure polarity perspective, we go, it should never happen. Water is very, 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 very polar. Oxygen is very, very, very nonpolar. Nonpolar bonds, nonpolar configuration. And yet oxygen is able to dissolve. Why? Because just enough of it is there to bend that oxygen just slightly to create a dipole, and that dipole allows it to go into the water and dissolve. The result here, we do get attractions that are stronger than intermolecular forces of London forces, but they're temporary. So this is why it is really important for aquatic life that the water be moving, because you need to have fresh interactions between water and the oxygen around it. If you don't, then the water starts to lose its oxygen over time, and basically your pond starts to dry up. Fish start to die in it. Depending upon the locale, you can get very brackish or salty. You can turn into a marsh, basically. So if there's no moving water, that's where this distortion kind of becomes problematic for aquatic life. So let's take a look at these dispersion forces and just kind of compare. So in terms of factors impacting the strength, again, size makes a big difference. The bigger they are, the more polarizable they are, the better their dispersion forces are going to be. The other big factor here is shape. And so what it is in terms of shape is we're really looking at surface area. How well are these molecules going to be able to interact with each other? Are they going to be able to stack on each other? Are they going to be able to get close to each other? That's where that distance bit that I kind of referenced at the beginning comes in. The closer they can get to each other, the greater their attractions are going to be. And so in terms of shapes, generally speaking, the best shapes are going to be planar rings, then non-planar rings, linear molecules, and then finally branched molecules. Now, this plays out primarily with organic materials more than anything else because that's where those shapes tend to be the most important. But you're going to see a lot of examples of organic materials in that skill builder you're doing later this week. So just looking at size, again, using boiling point as an analog for strength of force, the higher the boiling point, the stronger those molecules are attracted to each other. We can see that the bigger the atom gets, the more electrons it has, the greater its molar mass is, the more attracted it is to itself, the more likely it is to stay a liquid for a longer period of time. And that impacts not only atomic samples, but you can look and see the molecular gases do the same thing. So here's an example of an organic molecule, starting with 1 carbon here at the bottom, going up to 8 carbons here at the top. We can see that there is a general upward trend, not a linear trend, but a general upward trend in terms of boiling point. In terms of shape, again, higher surface area is going to create greater levels of attraction. Those greater levels of attraction are going to show up in the physical properties. So here is an example of looking at a linear molecule. Now, again, in terms of what linear means here, we're talking about a chain molecule where it is just one after the other, not in a sense that it's 180 degrees, but that we don't have different groups kind of coming at the top and the bottom of this chain. The more stretched out it is, the more surface area it has, the greater its attraction is going to be. So this one that has everything stretched out has a boiling point of 309. If I look closely, I can see that for this one, I just took this molecule here and attached it in the middle to get this second molecule in the middle. And that little change in shape dropped the boiling point by 8 degrees. Because not quite as much surface area available, the molecules aren't going to be able to get as close to each other. That extra distance is going to make weaker intermolecular forces. To get to this last one, same thing, just on the other side. All 3 of these have the same molecular formula. It's the shape that is dictating the boiling point difference. And this one that is the most clustered, most spherical, also has the least available surface area, and the boiling point really drops down by almost 20 degrees between the middle and the last. So that is where we will stop for today. On your way out, go ahead and hit the question here. And don't forget, assignment 6-1 is due tomorrow, but I would strongly encourage you to at least watch the video before you go into your lab tomorrow, just so that you have a better idea of how to analyze the data. Have a great afternoon.